Okay, so as mentioned, welcome, welcome, welcome. Okay, once the clock chimes, we will start. Okay, the clock chimes. Okay, so welcome, welcome, welcome. You see on the screen in front of you, this is our 5104-6104 module. Welcome to everyone. Then, as I was talking with my own PhD students earlier, they told me the GAs for our module. So I told them for this first class to actually be here lah. So I asked them to be here. So I'll ask them to say hello to you. So they are Mr. Wang Jiahui. Jiahui, can you please say hello?
Yeah, hello. Hello, hello, hello.
Okay, then also Miss Guo Hao Ren. Hao Ren, please say hello.
Hi.
Okay,
Hello.
that's how. Okay, then also Miss Xian Yuanjie.
Hello.
Okay, and also Mr. Zhu Zicheng.
Hello.
Okay, so they will be my 4 PhD students helping me in the module, and they will also be your GAs, and I will make reference to all these things even later on as we introduce the module. Okay, now before we start talking about all these particular things in the module, let me first of all go back to the canvas, right? Our module canvas. So if you look at our module canvas, okay, the most important thing in there which I put up, the rest of the things I didn't want to, no point, all those things are actually essentially in the README first file. So the other things I just put here. So as you can see, I mentioned very important to carefully read the README first file. Then just recently I added one more thing because department reminded us to mention these things. So final exam is definitely will be in person, face-to-face in some examination venue in NUS. All right, so you need to make sure that during that time you are here and will be able to take that exam. All right, because there are no alternative arrangements made. You will just have to, if let's say you have a medical situation, you have to submit medical MC because, and then you cannot say you're away and request for alternative. So this will be like normal. It's no longer pandemic kind of situation. It is normal kind of situation. All right, so that's quite important to remember. Okay, then some of the other things which I've posted in the announcement. Okay, Canvas requires you to click on every announcement. Okay, we click. So first one is to say that, okay, the module Canvas is open. All right, then I did note that there were various valid reasons, right? Various very valid reasons, and also because for today's class, I want to record it. All right, so I want to record it because there are some specific things specific to this semester. All right, because in lecture 1, although I will deal with the technical material shortly afterwards, in lecture 1 there are also some very specific things for this semester that needs to be mentioned. All right, including what I just mentioned just now, that the exam is confirmed to be in person, face to face. So again, that's stated down there very clearly already. All right, but also noting that there are among you all people who are working. So indeed, at least for my case, I will coordinate Prof. Pretty much last semester for our module, which is another one. He also took the same approach. that each class starts at 6:15. All right, to accommodate people who are rushing from their workplace. Okay, so this part to note that. All right, then this is where the GAs will be very, very helpful. All right, the GAs will be very helpful because with the material that we are doing, okay, I know that particularly in the later part, I was very, very supportive to approve many of your appeals, even though you all didn't have the prerequisite. Pretty much in the end, the only prerequisite that you appear to have is that you have done some signals and systems. I hope that is sufficient, but even for what we are doing today, some rather more detailed type of signals and systems things will come in, and you just have to decide for yourself, you know, whether you can manage it with what you have in signals and systems. Okay. Okay, never mind. So with that, this is how matters have turned out. So you have to look for yourself. You have to be very clear about whether with what you have, the material is manageable for you. But in any case, as I said, I've discussed with my GAs, and what we have made available is that okay, not tomorrow, but starting from next week. All right, starting from next week, Saturday, every Saturday for the next few weeks, Saturday, 21st January, 28th January, 4th February, 11th February, 18th February, 25th February. All right, from 3 p.m. to 5 p.m., Jiahui, Hao Ren, all right, they are the ones assigned to this. They will definitely be there in the lab, all right, in the lab, and for any materials in our module that are covered in the lecture classes, even later on in descriptions on the continuous assignment work, all right, that let's say you want to discuss in person, all right, these provisions are made available for you to come to the lab and discuss in person with Jiahui and Hao Ren. All right, so they are my own PhD students, and while they will be very familiar, they have taken this module before. They will be very familiar, so they will be there. All right, then for this specific time slots, for this specific dates and time slots, all right, my module coordinator, my lab manager, all right, will later be programming the electronic door access, so that for these dates and times, all right, all you need to do is go to the front door of E4A0304, all right, put your metric card onto the door and the electronic lock will open, and then you can come in. Okay, then basically Jiahui and Hao Ren right at the end, so that's why I say you enter by the front door and go right in towards the end, and they are stationed down there in the lab for all of these sessions, and ready to basically guide you on face-to-face discussions for any assistance that you need. Okay, so that's the additional arrangements that we've made. Okay, then in response to some further communication, so today I just further updated. So today our lecture is online via Zoom. Okay, my plan will be next week's class will be also online via Zoom. Okay, it's already programmed in the Zoom. All right, it's already programmed in the Zoom. You can see it. All right, so this is next week's lecture class, which is already programmed in the Zoom. Okay, next week 6 p.m. So, oh, okay. So that's next week, lecture 2. Okay, but lecture 3 will be in our classroom. All right, will be in our classroom. So the approach that we are taking is basically a mixed hybrid approach. All right, so it's a blended approach. All right, of online where appropriate, but there definitely will be physical in-person classes. Then, of course, whether online or in person, it starts at 6:15 p.m. Right? So that's the arrangement. Okay, then I've coordinated with my GAs and we've planned even further ahead. All right, we plan even further ahead. Later on, you will see as I talk in detail of the materials and about the how we will arrange the module, the grading, and so on. So we've already even I worked with my GAs and we already even scheduled ahead the briefing sessions to help you with your CA materials. All right, CA materials. So I will likely talk more about this afterwards in the proper thing. So you can see this is also programmed. This with the briefings, the additional briefings to assist you with your CA, that would also be online. All right, so as you can see, that's already planned ahead and scheduled. Don't worry, this will also be recorded in the Zoom recording. So you can play the recording again if, let's say, you want to refresh your mind on certain things and so on. Okay, so that is the way that we are essentially planning the work in the module. Okay, with that, let me go back to the README first file. All right, so as I said, important to look at the README first file. Okay, all these other things, relevant basic information, I'll just let you read. I'll just let you read. Okay, module syllabus is also below as you look in the pages. That one I will also pretty much just let you read. I'm not going to dwell on it. Okay, as I also mentioned to my PhD students, my GAs, I said today's class will be a relatively shorter class. It will be roughly 1 hour 45 minutes. So I wouldn't call a break. Okay, next week's class will be the full 3 hours. Full 3 hours, I will call a break in the middle. But today, 1 hour 45 minutes, what we'll do is we'll just handle the material and we'll just go straight through. Okay. Okay, so all these things I let you read, module syllabus I let you read. Okay, then come to the very, very important things down here, which certainly will be in your mind. Okay, how will the module be graded? Okay, this is how we will grade things in the module. All right, there will be two more, in some ways you could say more, okay, more compact. Okay, CA assignments. Typically, we will label this as CA1. I'll mention more in a moment. All right, we'll label this as CA1, which is from me. All right, then there's a CA2, which is from Prof. Ho. Okay, CA1 from me, CA2 from Prof. Ho. So this CA1 and CA2 together, they are worth 40% of the marks. So CA1 from me is worth 20%, CA2 from Prof. Ho is worth 20%. All right. So my one in the first part of the semester, as we develop the material, it will be quite clear to you what my CA1 will be. Prof. Ho's material will largely come about and be substantially developed in the second part of the semester, mostly after the recess week. But he will also assign it to you quite early, maybe after the break, after the recess, he will assign it to you probably 4 weeks or 5 weeks after the break begins. After the break, there are 7 weeks after the break. Before the break, there are 6 weeks. After the break, there are 7 weeks. So by about the 4th or 5th week after the break, Prof will already tell you about CA2. All right, so CA1 from me worth 20%, CA2 from Prof worth 20%. Then from my part, there is a CA3, and that's worth 30%. So 40%, okay, 30%, 70%. There will be the final exam. So remember, we've said the final exam will be in person, face to face, in an exam venue in NUS, right? And that exam will be worth 30%. Okay, all of you would already realize that the class, you all are 5104 students together with 6104 students. Okay, so no need to be too unduly worried, because we are very, very clear. Okay, 5104 is 5104, 6104 is 6104. All right. In the material that I cover, there will be some parts specific, more advanced ones specific to 6104 only. So when it comes to that part, I will mention that. Okay, and we are very, very fair. In the CA assignments, 6104 students will have more advanced CA assignments. All right. So same here for CA3. And then for the examination, it will be 2 different examination papers, a different exam for 5104, a different exam for 6104. Of course, 6104 will be much more advanced lah. Okay. Okay, so let me go back to the announcements again. So this is the latest announcement that I posted today. So basically for my CA1 and CA3, we will have online briefings to further guide you during the recess week. And then typically, as I would mention in this first lecture class, in writing the reports, all right, for my CA1, Propo CA2, and also my CA3, okay, we're not interested in you hurrying. We want you to do the work carefully, reflect on the work, maybe further improve on the work, do even more work. All right, so that's why it will always be the case that, all right, the deadline for submission of all the CA reports, we will give you all the way up to reading week. Okay, so remember in NUS terminology, reading week is very, very late. Reading week is the week just before exam starts. All right, it is in April. So the due date time deadline for all CA reports is okay going to be on the Wednesday, 10:30 a.m. of the reading week. Okay, so nearer the time, we will remind you. You also see here that I've mentioned that actually we have a lot of supporting materials there to already guide you. Okay, shortly I will show these supporting materials, which can be found actually in the folder, in my case, under assignments. Okay, very shortly I will go to that. Right, but before that, let me go back again to the read me first file. And then as in my usual way, let me again pause. So just at this stage, on how we organize the module, CA assignments, all the support that my GA, my PhD students will provide for you. Okay, just on these matters which I've just spoken on. Any thoughts, any comments, any questions on? Okay, okay, with that then, as I had mentioned, right, I said, okay, the CAs in my usual way. So there are quite a few students here which were from my class last semester. so they know what I'm talking about. This is my usual way. All right, not only do we provide you GA support, we also make sure that there are enough documents inside our files, which will be reference material to help you further help you in your working of your continuous assignment. All right, so as I said, if you now go to the folder, all right, for my part, the first part, all right, which is from me. All right, so now you will actually be able to see some of the things down there. You will see some of the sample CA requirements. This is not okay. This is not your assignment. This is a sample assignment from past year. In last time in the other online system, Luminous, I could put short notes to describe this file, but in Canvas, there's no space because previously I would just say that this is not your assignment. This is just a sample for you to see. All right, so this is a sample. Here's another. This is a sample for CA1. This is a sample for CA3. Then the other two, the additional two, are very, very detailed ones, which you can look at later when you are at the stage where you have finished the work and you want to write your report. Okay, so anyway, they're all here. I'll show you. So this is the sample CA1 report. This one is a yet different one, but this is a more recent one. This is for 6104. So it describes down there. It will not make sense to you at this moment because we haven't covered the material, but this would be the 6104 assignment. So this is a sample. 5104 has some similarities, but 5104 would essentially, if I remember correctly, just stop up to part D. 5104 stops up to part D, but I want the 6104 people to investigate more. And in this investigation, it's not just a question of just doing more work, but you should think about how the theoretical underpinnings of this work and the implications of this work. So 6104, I push you deeper. I want you to tell me much more about what's happening. So this is a sample. Okay, this is a sample. This is not yours. Later on, nearer the time, I will upload your actual CA1 requirements. All right, so this CA1, this is CA3. CA3 in the earlier years, what happened was that we actually work on the hardware, but never mind. Basically, in your CA3, what you are going to do, even though it's not actually on hardware, it is, whoops, oh dear. This is what actually does happen. Never mind, I know what to do. Okay, let me now instead open it with Chrome. Okay, this is also there inside your notes. Okay, so this is CA3, but from the earlier years when we were actually working on hardware. So your CA3 will be similar, except I convert this everything to essentially equivalent simulation aspects, where I also want you to capture some of the practical real-time aspects. But this just shows you, okay, that this is the equivalent of your CA3. Okay, then I really hope the Adobe doesn't give up. Okay, then as I mentioned, so those were the assignments themselves. All right, those were the assignment themselves. Then remember, I told you that we will give you very, very detailed. We will give you very, very detailed additional support notes, and this is here. All right, so you can actually see that in the file. These are under the additional notes. This one, you know, in previously under the old system Luminous, I'll put the notes there. Don't read this straight away. Read this only after you've done the work. So here I just remind it down here. Okay, so these ones are very, very detailed. This was more recently, maybe about so not so long ago, I asked one of my GAs at that time, Mr. Sun Lu. I said, look, write these things in detail. So this is very, very detailed for CA1. And you see Sun Lu has actually written out everything in detail in CA1, so that later on, out of memory. I don't know why, how come it can be like that? Okay, so anyway, in the file, you should be able to see it. All right, so Sun Lu has written this in great detail. And later on, when you actually finish your work, you can refer to this file for your CA1. And then when you when you finish your CA3, you can also refer to this other file from Sun Lu, which is very, very detailed. Again, anyway, you can see it. And that will help you in writing of your CA1 and CA3 reports. And you have lots of time, as I said, So as I said, our plan is to let you have lots of time to do a lot of very, very detailed work, very substantial work, and we give you all the time until the reading week, which is in April. Okay, so that's all the support that we have provided. Now, more than that, all right, more than that, if you go to lecture notes, all right, now, of course, today's lecture is being recorded since it's on Zoom, but some of the classes, right, some of the classes where I want it to be in person, in the classroom, my way of doing it is if I'm doing Zoom, I do it the Zoom way. If I'm doing it in person, I'll do it the in-person way. Okay, so the in-person classes will not be recorded, but never mind. As you can see, what had happened was that in previous semesters, the entire module, all right, no choice because it was pandemic. So everything was over Zoom. So that one had no choice, okay, had no choice. But now this semester in Singapore, we are no longer operating with pandemic. We certainly can have a blended approach whereby there will be real in-person classes. So as I said, in our case, not next week, following week will be in person. And okay, that will not have recording, but again, no worry, because if you now look inside my folders, you will see that I prepared ahead for that. I have a file down there, a WinWord file, all right, that if you download, you will see that here I have actually now put the Zoom links for all the past recording for my part. Lecture 1, Lecture 2, Lecture 3, Lecture 4, Lecture 5, Lecture 6 for my part. All right, so if you want, you can even actually look ahead. And when I check my Zoom account, I check the recording because I can see who has seen the recordings. And really, some of you, very on the ball, as we call it in Singapore, have already checked out and look ahead on some of the lecture classes. Okay, so to me, it's all right. I don't have a problem. I don't have a problem. All right. I welcome you to go ahead and prepare ahead. Okay, so you can go ahead and prepare ahead because these are all there. I'm not so worried about the later lecture classes. Okay, so lecture 3 for us will be in person in the classroom. But this will be equivalent because by that time of lecture 3, all the materials will be really technical material. All right, whereas for lecture 1, and even going into lecture 2, there are some administrative arrangements which I mentioned, which will be different from that time. Because that time, for example, we were using Luminous. So, what I said down there pertains to Luminous. And then what I said down there pertains to those kind of other arrangements down there. That year, so Xiaohui and Howren were the students in the class that year, okay, taking that. That year, no, I didn't have GA support on Saturday. I didn't have, because that time I took a different approach. So they all had no availability of GAs to discuss on Saturday afternoon. So now you have. So as I said, for lecture 1, lecture 2 class arrangements, there are specific arrangements. So some of these which were said in last year are not the same as what I say here today. But anyway, these are available. So with that, then pretty much we are very, very well prepared. So again, to say that, look, okay, this is the way that we will do the grading. Then you've seen also in the announcements, I state in detail the arrangements. All right, and also the deadlines, right? Deadlines. Also GA support, right? So all these are down there, which are new for this semester. Okay, so with that, then let me again, as usual, pause for a while and check whether anyone has any thoughts, any queries. Okay, if not, then as I said, today will be a relatively shorter class. I will develop actual technical material. But even though the material is actually drawing from a very specific basic example, but if you now look carefully at the ideas in there, this will be the very key ideas that are already there in this method of taking an approach to adaptive control. All right, and you will see down there the types of ideas in signals and systems which actually go in very, very detailed ways. So as I said, in the recent weeks, quite a few of you, you didn't have the prerequisite, you appealed, and we were very kind. We just said, okay. But you now have to decide for yourself, once I develop the material, whether, the kinds of signals and systems that you have would be the kind that would be the background that would be needed. Okay. So anyway, I'm glad to have all of you. I think almost everyone is here, because when I look up in my other screen, because I can monitor, essentially looks like almost everyone is here. But anyway, we'll start. And in any case, the material is being recorded anyway. So with that, then, well, the students in the class here from my last semester, they would be very familiar. As usual, what I would do is now I would start developing the material by hand. Okay, what you would need to do, if you have not already done, is to go to the additional notes, right? And then pull up this one, the note 01 pre-class file, which will be essentially the same one which I have here. And you will see that the file is incomplete. In the class, I will now develop the material down here. And with that, this is what I'm going to do. All right, this is what I'm going to do, and I'm going to develop the material, which is what I'm going to do starting now. Okay, so this method of adaptive control, right? This method of adaptive control. So essentially, as we look at it, we can actually motivate it in some very simple way. We can motivate in some very, very simple way. All right. So as I said, just motivate it by looking at this very, very simple arrangement down here. Okay, look at this very simple arrangement down here. So as would be quite typical in formulating a control problem, you would say, look, I have a system I want to control. And in this case, I will even start with, almost the simplest type of thing you would encounter in signals and systems. Right? I would say, okay, you start with this. Okay, you want to control this, and I'll just say, look, this is basically the first order system. YP dot equals to APYP plus KPU. All right, so YP is the output signal you have. U is a signal that you're able to manipulate going into the system that you have. And typically in the control problem, all right, what you might say equivalently in various different ways, right? In various different ways, you might say, look, okay, this particular system that I have either is very slow or it could even be unstable, so it's not very nice to use. Really, I want to be able to control it, right? Really, I want to be able to control it in such a way that, all right, ideally, if I put in a command signal, all right, because in control system, you would want to put in a command signal to request your system to change from one setting to another, all right? And that would typically happen, right? Let's say, for example, that's why it's quite interesting previously when we had the actual hardware, right? When the actual hardware, for example, you might work with a motor and you might want to say, look, basically what you might want to do is you say, look, what I want to do is when I put in a command signal starting from the motor, all right, at position 0 degrees, all right, I want it to move at the end to 30 degrees. I expect that at the end it will move from 0 degrees to 30 degrees. Okay, here you are seeing the time when they did the experiment and the adaptive control has completely worked. This is what they're able to see. So you can see, they say they want to put this position, and you can really see it is really moving exactly as what it is. So essentially, is that kind of situation. You're saying, look, when I put in a command to my system, okay, let's say it's a positioning device, it's currently at 0 degrees. When I say I want it to move to 30 degrees, I want a response like that. It will really move from 0 degrees to 30 degrees with some kind of reasonable response. Let's say, like, maybe in about less than half a second, especially if it's a big system, it should exactly move from 0 degrees to 30 degrees. And you want it like that. Except that with your system, if it's a slow system, it may not move so fast. Even worse, if it's an unstable system, it's not going to do this for you at all. Okay? Because you said, I want to set a command signal to move from 0 to 30 degrees. And you say that at the output, I expect that it will move from 0 to 30 degrees with some kind of response time, which I specify. Okay, let's say, in half a second. All right, so that's exactly the control problem. And we are not even talking about adaptive control yet. All right, we're just talking about the typical control problem. Okay, how might we do this if it's a control problem? All right, so remember, I'm not talking about adaptive control here. I'm just talking about the simplest. Control problem. Okay, so how might we do that? Okay, so that's quite clear, because this is our system given to us, and if we say that we expect that at the end of doing all the control that it should be behaving like this, the moment you say you expect that it's behaving like this, you have also just told me that, all right, what you want is you want a certain response coming out of your specification, and that comes as, all right, AM, YM, all right, plus KM, RT, which is your command signal. Right, and you can see because it would be like that. It would be like that because if you look at your specification down here, right? If you look at your specification down here, you just told me that you put in a command signal moving from 0 degrees to 30 degrees, you expect it to move like that. All right, you've just told me the response time. All right, and you also say you want it to move exactly from 0 to 30 degrees, which means that you also told me that in the steady state, you better have unity steady state gain. And that is all completely now described in AM, which would be your response time, and KM, which would be your unity steady state gain. Okay, so that has to be described down there already. And then for this simple system, for this very simple system, right? For this very simple system, okay, for this very simple system, to get this kind of a thing, all right, okay, it is quite straightforward to say, okay, to get this kind of thing for a system like this, I can take my measured output signal, feed it back by a control gain, take my command signal, okay, multiply it by a scaling gain, all right, and if I can calculate the correct numbers, I will be able to match that. So that's quite obvious because, in this particular setup, it's very clear. It's very clear that, okay, that basically what is needed is a control signal, which is U equals to some gain, theta, times yp of t, all right, plus some scaling gain, all right, times the set point signal. All right, this is just a starting point, and this is really starting from your undergraduate control, some of which were in my module last semester for my students who are here. I mean, this is just exactly what it is. Okay, then we can push on further. Okay, if you now take this, all right, and substitute it back into your actual system, or you can substitute that into the actual system. Okay, which is what we would do. Remember, I'm not doing adaptive control yet. I'm just motivating it by the very simple, straightforward, typical control problem that we would face. So this will be, I just substitute this in. This will be theta yp of t plus k times r of t. All right. And then basically you can clearly see, all right, that I can substitute all these things in. All right, and once I substitute all these things in, you can clearly see that, all right, you can clearly see that, okay, it will be like this. It'll be like this, and clearly there will exist, right? Clearly there will exist suitable Kp and theta such that this will be the AM that I desire, and there will exist a Kp such that this will be the Km that I desire, right? And if so, then okay, one moment. All right, if so, then what will happen is that this would be those exact gains that would work. All right, and then if I go on further and simplify it, all right, then this will exactly get me, as I said, AM. I'm not doing adaptive control yet. AM yp plus km r of t. All right, so I'm not doing adaptive control yet. I'm just motivating the problem. Okay, also maybe at this stage to mention to you all, because the students who are in my last semester class, they know, okay, at the end of this evening's class and at the end of every evening's class, I will also upload the complete version of my fully handwritten version. So don't worry if you miss out some of the handwriting, because I will upload it for you. Okay, so put your mind to that. Okay, so then this will become like that. All right, this will become like that, and obviously in the whole arrangement, right? Obviously in the whole arrangement, clearly we will be right. We will be interested. Okay, if these are the correct gains, we'll be interested in the tracking error, right? So we'll be interested in the tracking error. So here, even at this stage, we're not doing adaptive control yet. Okay, we say, okay, we're interested in the tracking error, and it'll be like this. And then, of course, if you specify your AM and KM, all right, because in how you specify your AM and KM, if you specify your AM and KM via this desired performance, obviously this is a stable system, so AM is gives you a stable system, right? So if you now look at what the tracking error looks like, tracking error E1 is yp minus ym. Then we take the first derivative E1 dot x is yp dot minus ym dot, and then you go and simplify that. All right, and then clearly this is now am E1 of t, which is the tracking error. Okay, so that's straightforward, and that's nothing more than, there's nothing more than just starting from your undergraduate control. Okay, so I'm not doing adaptive control yet. Okay, now we start. We said, look, this is exactly what we want. This is exactly what we want. All right. And if we know the correct numbers that we put in, then it will be exactly like this. All right, it'll be exactly like this. Okay. And then what would happen is that it will be E1 dot equals to AM E1, and AM is for a stable system, so the tracking error will die away. Okay, so this is not yet adaptive control, but it's a simple problem from your undergraduate control. Okay, now we start. But okay, we said no, we are no longer going to follow it like your undergraduate control. We will now start with this simple problem, but we said, oh, it will be no longer the case that we know exactly what this AP is and KP is, because you know exactly what AP is and KP is. You know the numbers to put in exactly in here. You know the numbers exactly to put in here, right? You know the numbers exactly to put in here, and then it will exactly get you what you want, as we saw, right? You know the numbers to put it in here, get you exactly these things, and it will work. All right, that tracking error will go to 0. Okay, but we said no, we're not going to do the things you did in your undergraduate. We're going to say, look, we're going to look at a situation whereby we don't know AP and KP, and we still want to get the same result. We still want to get the same result. So this is where adaptive control starts. All right, this is where adaptive control starts. Okay, so since we don't know AP and KP, there's no way that you'll be able to calculate those exact perfect gains that you need. All right, those exact perfect gains that you need, because you don't know AP and KP. All right, if you know AP and KP, you can calculate them so you can get those exact gains, theta star and K star. But you don't know, and you still want to get the same kind of performance. Okay, so we said, okay, you want to get the same kind of performance. So we back up a bit and we said, look, we still look at this arrangement. All right, if we know AP and KP exactly, we know exactly how to calculate this. But we don't know AP and KP, and we still want to get the same result. Then we stare at this, we said, look, even though we don't know AP and KP, at least we know this structure works. You put in some number theta, you put in some number K, even though you don't know it, but we know this structure works. Because if you put in the exact numbers, it will get the result that we want. So we know this structure works. So we say, okay, since we want to get the same result, even though we do not know exactly how to calculate the perfect control gains, we will just continue to use the same structure. So we just continue to use the same structure. So then, if we continue the same structure, so our control signal is still theta times yp of t plus k, the scaling gain, times r of t. All right, but we don't know how to calculate it. All right, but we know the structure works. Okay, but since we don't know how to calculate it, how about making this varying? All right, so now you see that these gains are now time varying control gains. All right, they are time varying control gains. Okay, so I want to make this time varying. If I make this time varying, I must tell you how I'm going to make this time varying. Okay, how I'm going to make this time varying. Okay, here I'm going to just write this down and tell you how I'm going to make this time varying. Okay, later I will show you the basis for it, which is the entire thing we'll do this evening. So I put in time varying gains because I know this structure works. And since I make this time varying gains, I must tell you how to make this time varying. Okay, so I tell you how to make this time varying. I say I will now make this time varying in the following way. And this is what I call my adaptive block. So I need to tell you how to make theta time varying. I need to tell you how to make k time varying. I'm going to make them time varying in the following way. I'm going to update theta. All right. I take the tracking error because whether it is adaptive control or whatever, is still the same diagram. I'm still measuring the output signal. I'm still specifying the type of performance that I want. All right, in the performance that I want is already specified. This is specified by me. This is specified by me. All right, so it's still the same arrangement. It's still the same arrangement. Okay, for my system, I still can measure the output. I specify the performance that I want. So I build this dynamical system. All right, I put the reference signal in there, then I can see the reference output signal. I can still measure the tracking error. All right, even though my gains may not be correct, I can still measure the tracking error. So I measure the tracking error and I call it E1. All right. And in how I'm going to adapt it, I'm going to take the tracking error, multiply it by the output signal, multiply by a positive gain signal, gamma 1, any positive number. Here it turns out that I need the sign of KP. I'll say something in a moment. So this is how I adapt my theta, update my theta. This is how I update my K. I take the tracking error, okay? I take the reference signal, all right, because I have the reference signal, all right, in my system, I have the reference signal. I take the tracking error, I multiply it by the reference signal. I multiply by a positive gain gamma 2. Also, the only condition I need is it needs to be a positive number. Then I also minus take signum KP. All right, in this simple way that I'm doing adaptation, okay, I use this additional bit. So here what is happening is that, all right, although I say that I don't know the numbers AP and KP, in this first simple way that I'm doing adaptation, I don't know the sign of KP, but I say at least let me know the sign of KP. Sign of KP is not difficult, okay? For large class of practical systems, all right, what you can do is you can simply put some kind of a step in there. Then you see what direction the YP moves, all right? If the YP moves in the positive direction, KP is positive. If the YP moves in the negative direction, KP is negative. So a simple experiment actually can get for you this sign of KP. All right, for this first simple way, all right, for this first simple way of doing adaptive control, and I'll show you, all right, in the rest of what we do today, why this works and how this works. Okay, okay. If you don't like this, it's also no problem. All right, it's no problem, but it does turn out that it's not a simple problem to get rid of sign of KP. In the early years, it was even thought that this knowledge of sign of KP was what was termed as a necessary condition. But it turns out that no, it wasn't quite a necessary condition. It's just a sufficient condition. All right. And for a long time, people tried to see how to solve that. And it was an entire PhD thesis. It was an entire PhD thesis just to be able to work on handling this sufficient condition. All right, and if you want to look, all right, for those of you, particularly those 8 of you in the class, there are 8 of you in the class doing PhD. If you want to look further, you can look under the idea of Nussbaum gains. All right, so you can replace that with what is called a Nussbaum gain. Okay, and it can remove the condition for you on sign of KP. So mathematically, it removes that, but in terms of real performance, replacing it by Nussbaum gain, although solves it for you theoretically, but your performance deteriorates. Because what the Nussbaum gain does is that it basically searches in both directions. In fact, it searches, when it comes to a multi-dimensional system, it searches in n space. All right, so you can basically project it from signals on a torus. Okay, and then what happens is that not only has it got to search in the entire n space, and as it progresses, it has to search faster and faster and faster and faster. So it's a lim sup, lim inf kind of a problem. All right, it's quite interesting. All right, so it solves it, but in terms of performance, because you can see it is, basically having to search all over. Meantime, as you search in the wrong direction, your control is getting worse and worse. Finally, it converged, but meantime, your control is very bad. Whereas if you practically are able to do a simple experiment to do that, your control approaches beautifully straight away. And you can, it's actually like this. So this is actually, taking a simple step on the motor to see the sign of the KP, and then you can see, this is the moment they start the adaptation, and you can see, and this is real experiments. This is not simulated, real experiments, and you can see, the performance actually gets done almost straight away. Whereas if you use the Nussbaum gain, the first part of your performance will be very horrible. Okay, but never mind. This is just alluding to some of the ideas here. Okay, so now remember what I'm saying is that since we do not know AP and KP, but we know the control structure work, so we use the same control structure. But since we do not know what gains to use, we make the gains time varying. But since we make the gains time varying, we have to specify how to make them time varying, and they are specified to be time varying in this particular way. All right, in this particular way as a first simple way. Okay, now we have to show you how this works. And this is where you can no longer talk about S-plane, right half plane, left half plane. That's why I said I'm a bit worried when I approve some of the appeals. It's no longer about left half plane, right half plane. All right, it's no longer talking about Rao-Hurwitz criterion, root locus. None of this will work. None of this will work. Okay, so instead, okay, we have to do it differently. So how does this work? Okay, so we look at this and we said, look, this one, we can no longer talk about left half plane, right half plane. We can no longer talk about root locus. Okay, so what we say is that let's look at the problem carefully. What would be the signals of interest to us? Okay, the signals of interest to us are clearly tracking error. All right, of course, I'm interested in the tracking error. And even though I'm making this time varying and adapting, all right, so I put this as a gain. And since I don't know what perfect gain to put, I make this time varying and adapt it. I put this as a gain, time varying and adapt it. But even though I'm adapting it, even though I do not know exactly what the perfect gains are, remember the perfect gains exist. For a given system, the perfect gain exists. The perfect gain exists, just that I don't know what they are. All right, but never mind, they exist. So since this is the gain that I put, these are the gains that exist, I can always define a parameter error signal in my theta of t, because ideally I would like my theta of t to be theta star. Ideally, I would like my k of t to be k star. So I can define, all right, the parameter error in theta. I define the parameter error in k. And clearly, this will be the signals that I'm interested in. All right. And if I'm interested in the signals, one way to look at how this system is working, one way, all right, one way may be all right, one way may be to say, okay, since these are signals of interest to me, let's look at some kind of, the simplest way is to say, convert this to a mathematical energy function, all right? Mathematical energy function. So clearly, all right, I would be interested in an energy function that would be like this. All right, clearly I'm interested in energy function involving the tracking error, E1 squared, all right? I'm clearly interested in the energy function, which should also capture, all right, the parameter error in theta, p squared. And I should also be interested in the remaining signal, all right, which is the parameter error in k, so I call it c squared. All right, except that my energy function, I have to shape it correctly because it is not going to be easily a spheroid in n space. All right. Because that would be the most natural, but it's not going to be a spheroid because there are various numbers involved. And it turns out that we really need to kind of shape it. And the correct way to shape it is to put magnitude of Kp over gamma 1. Remember, gamma 1 was the control gain, right? The positive control gain that I use for theta. There's gamma 2 as well. All right. And Kp was from the system, all right? The system, my system that I try to control. I don't know Kp. I don't know Kp, but never mind. Here I'm just philosophically stating, all right, an equivalent energy function of interest. All right, so I put it down there. So again, this will also need to be shaped by magnitude of Kp over gamma 2. Okay, remember, I'm just using this thing for analysis. Okay, I'm just using this thing for analysis because I don't have the number Kp. I don't have the number Kp. All right, in any case, I cannot measure P and C, which are the parameter errors. But it doesn't prevent me from, you know, writing this ellipsoid down. This is an ellipsoid, basically. All right, doesn't stop me from writing this ellipsoid down as a signal of interest to me. All right, so now if I look at it, clearly, the errors in the tracking errors are here, the parameters errors are here. And then I can say, look. Why don't I look at this system and then see for this signal how, all right, then see for this signal how this ellipsoid signal for which I'm interested in is changing with time. And if I say that, if I say I'm interested in how it's changing with time, then I'm saying, look, I'm looking at its time derivative. So I need to take time derivative of this whole thing. It's quite straightforward, basically. You know, this is E1 squared, you differentiate this, right? This is P squared, you differentiate this, is C squared. So you differentiate this. So if you differentiate this, is quite straightforward. So remember, we have put half down here. So you differentiate this is 2E1 dot, right? You differentiate this is 2 phi dot, 2 C dot. So we put it down there. All right, and then if we differentiate this down here now and you write it out, this will now become the half and the 2 cancel. So this will become E1 dot, all right, plus magnitude of Kp over gamma 1 P dot plus magnitude of Kp, all right, over gamma 2 C dot. All right, so you can check this. That's quite straightforward. Working on the derivative down there. Okay, now let's begin to take all these signals down here which has come up in the time derivative. All right, so first of all, let's look carefully at E1 dot. All right, let's look carefully at E1 dot. E1 dot is E1 is Yp minus Ym, so E1 dot is Yp dot minus Ym dot. Okay, then with that, let us carefully look at this whole thing. All right, Yp dot is APYP plus Kp. Remember, it was Kp theta. We put in theta as a time varying gain. Theta times Yp plus Kp. Then the other one, K, all right, times R. So I'm just exactly writing this down here, except that, you know, what I'm going to do is I'm just going to expand it out because instead of theta, I write theta as, all right, the exact theta star, all right, plus the error signal. All right, so you can go and double check. You can go and double check that, you know, theta star plus P of t is exactly theta. Right, so in the same way, for K of t is just K star, all right, plus P of t, which is the C of t, which is the error. Okay, so I have that. Okay, so I have that. And then this one, simple exercise. I mean, basically today, some of the materials, not that difficult. Simple exercise. I'll let you go take this now. All right, work this through and simplify it. If you simplify it, all right, you will find that this now will turn out to be AM E1 of T. All right, because remember, All right, remember that, all right, you can take Kp theta star combine AP plus Kp theta star is going to be AM. Then Kp K star is going to be Km, leaving you with the errors. All right, so anyway, if you simplify it, you're going to get AM, all right, plus Kp into this whole thing, which is P of T times Y P of T plus C of T times R of T, all right? And that would be the expression simplifying E dot, which we will later on put it in here. All right, we'll later on put it in here. Now, let's go on further. Okay, clearly in this expression down here, you also see we have C dot, P dot, and C dot. Okay, let's also look at it. All right, let's look at it carefully. Okay, you will see that P dot, right? P dot, P is theta minus theta star. All right, that's the parameter error. All right, theta star is a perfect number. It's just a number. Theta star dot is 0. So P dot is exactly theta star dot, which is minus signum Kp gamma 1 E1 Yp. That was how we set up the adaptive law. Similarly, C dot is basically parameter error K minus K star. Right, same thing. That would turn out to be minus signum gamma 2 E1 times R. Okay, so you have that. Okay, let's substitute all of that into the above expression. If you substitute all of that into the above expression, you will now see this is now going to be AM E1 plus KP PYP plus KP C times R. All right, and then this other one, of course, is also here. This is now minus signum Kp, all right, minus signum Kp gamma 1 Yp E1, all right, and that one is minus signum Kp gamma 2 R times E1. Okay, and at this stage, all right, basically this is the basis of the design of the adaptive controller that we have in this development down here. All right, and in this design, all right, this is basically the basis of the design because it actually is the main thing down here. If you look carefully at this, all right, you look carefully at this, the sign of a number, so this is Kp, the sign of the number, times the magnitude of the number, sign of number and magnitude of number gives you the number itself. So this is minus Kp now. All right, then gamma 1 cancels. So this is now minus Kp P Yp E1. All right, which now if you look at it carefully, all right, this thing here exactly cancels out this term down here. All right, and that's the basis of the design equation. Okay, for those of you, I know some of you have already taken 5101, and in my 4302, because you know it's an undergraduate module, we couldn't put in everything because we have to put in the nonlinear part. But in the early days, if you look in my 4302 notes, you will see we did reduce order observer. All right, if you 5101, you should have had the time to do reduce order observer. You will see the design of the reduced order observer is exactly like this, where you now look at the whole thing, and then you take the thing to handle the non-sign definite terms. And that's exactly what is being done down here. It is the same design technique. Okay, so likewise, if you check this carefully, you will see that this term here exactly cancels out, is designed to exactly cancel out that term down here. All right, once we have this arising out of our design, you will see that what we now have is, we now have the fact that the way that the ellipsoid V is evolving is V dot is going to be just AM E1 squared of T, and clearly this is less than or equals to 0 because by design, your reference model should be a stable reference model, and therefore A should be a number less than 0. So what you're now getting is that the ellipsoid has time development, all right, and it develops such that, okay, V dot is always less than or equals to 0. And we're not done because, you know, you really have to do your signals and systems very carefully for these things. And a lot of times, even for people who did adaptive control for research, they reach this stage and they think they are done. They are not. They are not. Because you really now need to go on to look carefully at this. All right, because, you know, first of all, we don't have the time to look at this. All right, in our module. First of all right, if you now look at these things, okay, the control law has time varying gains, but never mind. Even though the adaptive law is so simple, this adaptive law is very simple. All right, but you look carefully, this is YP. What is E1? E1 is YP minus YM. So basically, when you multiply out, there's YP squared. So even though this is a very simple adaptive law, if you like, it contains a YP squared term, which means that the dynamics are not linear dynamics. And if you want to be very careful, particularly for the 8 PhD students, if you need to do your work very carefully with this kind of system, first of all, you need to show that, you know, basically your system obeys a Lipschitz condition, that there is no finite escape, because in nonlinear systems, right, linear systems, even if it's unstable, it will go unstable at, you know, at most in an exponential fashion. It cannot go faster than that. It's just exponential. And when you have an exponential unstable system, at any point that you look at it, there's still a signal. The signal may be large, but there's still a signal. It's just exponentially growing. But for nonlinear systems, even a nonlinear system so simple as this, I can construct for you a simple one-line nonlinear system, which will escape to infinity in 1 second. And don't say 1 second. If you want it less than 1 second, I can make it less than 1 second, which means that the signal in finite time escapes to infinity. And that's called the phenomenon of finite escape, which means that it's not like a linear system whereby even though it's unstable, at any time you look at it, there's still a signal. For nonlinear system, you know, if I construct for you this system that escapes to infinity in half a second, after half a second, there's no signal. It's gone. So that's why, particularly for the 8 of you who are doing PhD, if you want to do PhD, you have to show us that, look, you know, if obeys Lipschitz condition, there's no finite escape, that solutions exist. Okay, basically it's about existence of solution. So pretty much in here, even though I have not told you for this simple system, I have shown you existence of solution. All right, I've shown you existence of solution and there's no finite escape. All right, so now, okay, now we look at the whole thing carefully. All right, it's all here, it's all here. Okay, I start off by saying, okay, this ellipsoid is of interest to us. I start off by telling you this ellipsoid is of interest to us. Okay, you stare at this thing carefully. This is just a number, even though you may not know number. Gamma 1 is just a number. When you start at the time when you are doing your adaptive control, let's say you started your adaptive control when we started class at 6:15 p.m. You started your adaptive control. At the time when you started your adaptive control, you started your system, YP is some number. It may be large, but it's some number. YM is what you generate as a stable system. So YM is a reasonable number. So E1 is whatever YP was at 6:15 and YM was at 6:15. So at that time when you started, YP minus YM equals to E1 was a number. At that time, you know, theta minus theta star, you put in some number to start your controller. You put in, if you don't know, you put in 0. If you want to put in a gain, okay, equals to 10, no problem. You can put in any gain that you want. theta minus theta star. At 6:15, when you started the adaptive controller, theta minus theta star is a number. When you started the adaptive controller at 6:15 p.m., k minus k star is a number. At time 0, this ellipsoid is just a number. The number E1 squared at 6:15, the number P squared at 6:15, the number C squared at 6:15. At that time, it has a number. It has a number. And then we've just finished showing you that by doing the adaptive law and the control law, we've shown you that starting from 6:15 p.m., when this was just a number, that this number will never increase. Because this number will never increase. We just finished showing you that. Okay, so that's why I said your signals and systems that you told me from your prerequisite, you have to listen carefully. It's probably all there, but you would have done signals and systems differently. Okay, so starting at 6:15 p.m., this was just a number. Then after we do adaptive control, I guarantee you this number never increase. What does that mean? So straight away, since I guarantee you this number never increase, I've just finished guaranteeing for you that in my adaptive controller, my signals down here, all right, the tracking error, the parameter error for theta, all right, the parameter error for k, these are all bounded numbers starting from 6:15 when I start, because starting from 6:15, when we started the adaptive controller, this was just a number, and this number will never increase because I've guaranteed you that. So since I've guaranteed you that, this number can never escape to infinity because look, it cannot even grow. This overall ellipsoid, okay, not just the individual numbers. All right, so this number can never escape to infinity. This number can never escape to infinity. This number can never escape to infinity. So this is the first result that I've gotten you. Okay, the second result that I need to tell you is, okay, I need to go further because it doesn't stop there. So I also earlier had noted that V dot is AM E1 squared. I would take that further because I need that further. So now this is AM E1 squared, and as I said, you will set up your reference system, your specification that you want as a stable system. So AM is a negative number. So to avoid confusing ourselves, I just change this AM to minus alpha, where alpha is a positive number, so we see that very clearly. All right, this is the expression that we got. We got this expression. All right, we got this expression. Okay, let me work on this expression some more. Okay, I will take this expression and I will integrate this expression. So I integrated it starting from 6:15 p.m. This was when we started. Starting from 6:15 p.m. to any time. All right, similarly, I integrate the left-hand side from 6:15 p.m. until any time. Okay, then I will now integrate it. Let me now integrate it. And okay, if you now follow properly the rules of integration, this is a definite integral. All right, so now when we integrate this, this would simply turn out to be V of t minus its value when we started at 6:15 p.m. Right? And the left-hand side, I will leave it as it is. Okay, our left-hand side, I leave it as it is. Then I rearrange. I will rearrange. Okay, let me rearrange. If I rearrange, I bring this over. This is positive now, okay, so that we don't get confused. From 6:15 p.m., I start to anytime. All right, so E1 squared d tau is just equals to whatever the number of this ellipsoid. Remember this ellipsoid? This is the ellipsoid that I started off with. Whatever I started at 6:15 p.m. with this number. All right, so this started at 6:15 p.m. This is just a number. This is just a number at 6:15 p.m. because at 6:15 p.m. you have a particular value for the tracking error. You have a particular value for the parameter error for theta, a particular value for the parameter error for k. All right, you have that. So this is just a number. Okay, so now this is how the ellipsoid is evolving. So I've just taken this and rewritten it like that. And these are obviously positive numbers because it's ellipsoid. This is also a positive number. Okay, then I take it conservatively. It's a positive number taking away from this positive number. I just throw this away. If I throw this away, then it's bounded from above by VT0. If it's bounded above from VT0, let me now rewrite this, all right, completely. All right, now I bring the 1 alpha over. let me use a different color. Orange. All right, so I bring this over 1 over alpha. Remember, alpha is a positive number. V at 6:15 p.m. is just a number. It's just a number. All right. So remember, this is just a number, positive number. This is just a number. All right. So since these are not just numbers, nothing to prevent me from writing this as just another positive number, C1. Okay. Now stare at this very carefully. This expression now that I've reached after working so hard, and this is just for a simple adaptive control problem. After working so hard, okay, this expression that I reached, it tells me that in the way that we have been doing adaptive control, we started at 6:15, we started the adaptive controller, started at 6:15. And if you now look at the tracking error in the way that we are doing the adaptive controller, remember the tracking error is yp minus yn. Is yp minus yn? Okay, never mind, don't worry. It said my pen power low. I'm very, very well equipped. I will just use another pen. Okay, this is my second pen. Okay, so now it tells me that in the adaptive controller that I started at 6:15 p.m. All right, this 6:15 p.m. And if I look at the tracking error and I monitor the tracking error for any time, up to now, I can even leave this tracking for up to next week, lecture 2 class. All right. And even further than that, it says you start at 6:15 p.m. today and you track it for any time, up to now, you know, up to next week, lecture 2 and so on. Just this is anything. It says that as you track this tracking error is always constrained by this expression to be less than a constant number. That's a constant number. So now you look at this and then you say, look, so what kind of tracking error signal obeys this kind of condition? And we need to do that. All right, what kind of signal obeys this kind of condition? So let's look at it. Okay, so let's say, for example, that we look at one signal. All right, so now we are looking at, remember we're looking at the tracking error, okay, what it may be, okay. So let's say we look at some tracking error, okay. In the beginning, it starts, you're doing 6:15 p.m., you start, it grows, and it goes like that, it grows like that, and then it continues. You look at this kind of signal. Can it be this kind of signal? It cannot, because, you know, in the way that we are doing adaptation, the way that we're doing adaptation has guaranteed that our tracking error obeys this condition. All right, in the language of signals and systems, this is a square integrable signal belonging to the class of L2 signal. All right, so I don't know whether your undergraduate look at L2 signal. Okay.
那这是事实啊。
Okay, so I don't know whether your undergraduate or whatever your signals and system look at L2 signals or not, but L2 signals will come out. All right, so this is an L2 signal, all right, belonging to the class of L2 signal. Okay, so our adaptation has guaranteed this. Okay, so what kind of signal can obey this? So clearly it will not be this kind. Okay, it may be this other kind of signal. Okay, maybe this other kind of signal. So in the beginning, okay, you know, when you're doing adaptation, okay, maybe it grows a bit, grows a bit, grows a bit. Okay, then it has to die away. It has to die away and just pretty much almost stay at 0. Because what has to happen? The type of signal that would belong to the class of capital L2 signals would be, okay, it can be, you know, very large, but at some point it must stay and be almost at 0. All right, because, you know, at some point it can accumulate integral, but as it accumulates integral up to the value of near C1, it cannot accumulate integral anymore. So only such a kind of signal, all right, it accumulates integral in the beginning. But after that, it cannot accumulate signal integral anymore. So this is very good because then it tells us that in our adaptive control, what is happening is that in the beginning, your adaptive control is not working, but this tracking error. All right, as you adapt more and more, in the end, what will happen? Tracking error will go to zero. And that's certainly, what you would expect of the class of L2 signals. But we're not finished yet. We're not finished yet. Okay, because an L2 class of signals can be like that. But okay, particularly for those, again, 8 of you who are doing PhD, when you're looking at signals and systems, L2 signals are like that. But because integration properly is defined by measure theory, all right, so you really have to look at measure theory. Okay, it is not approximation. So basically what happens is that L2 signals can be of the blue one, and the blue one can be like that. All right, combined with signals like this, whereby the signal suddenly spike, the signal suddenly spike, the signal suddenly spike, and so on. Because this type of spiky signals on the time domain, their measure is zero. They do not accumulate integral. So that's why it's still dangerous, and we are not done yet, because if your adaptation is not done properly, you can be looking like this, and most of the time your tracking error is zero, but suddenly it can spike, suddenly it can spike, because L2 signals include this kind of signals. But fortunately here in our case, we can go further because our L2 signals has this additional property, and we look at it from the tracking error. All right, tracking error you saw before we analyze this. E1 dot is AM E1 plus KPP. Oops, sorry. KP YP of T plus CR of T. All right. You saw we had this expression. Now stare at this expression very carefully. AM is just a number. E1 we have just shown to be bounded. E1 is bounded, P is bounded, C is bounded. AM is just a number. E we have shown to be a bounded signal. KP is just a number. Phi we have just shown to be bounded above. YP is equals to E1 is YP minus YM. E1 is bounded. E1 is YP minus YM. E1 is bounded. YM is bounded. Therefore, YP is also bounded from what we have proved above. We proved E1 is bounded. E1 is YP minus YM. YM is bounded. Therefore, YP is also bounded. P is bounded, YP is bounded, so this is also a bounded term. KP, C we have proved to be bounded. R, of course, your reference signal will be bounded. So we have just, in addition, shown that separately that the tracking error E1 dot, all right, the derivative of the tracking error is also bounded. All right, since we have now also that E1 dot is bounded, all right, since we also have that E1 dot is bounded for all T, all right, greater than from whatever you started off with, all right, is bounded. All right, then these two things together, all right, the fact that you have this L2 result, all right, you have this L2 result, and you have this boundedness result on E dot or the L infinity result. Okay, together these two things now finally imply that, okay, indeed in our adaptive controller we got what we want, that the tracking error indeed is guaranteed to be going to zero, which is what we want. Okay, with this, as I said, today's class, I'm now done. I will later on upload everything. I will upload everything that I've written by hand also, so you have the complete set of things. All right, you have the complete set of things. And then I look forward to see you all for next week's class. So remember, for next week's class, we will still do it by Zoom so that I can record it, but also because some of you, there are different arrangements, so this would work out. But remember, lecture 3 will now be face-to-face in the classroom. Okay, so let me now stop recording.